Lesson 2.4 is a lesson on continuity and discontinuity. We're going to begin by looking at some examples, and if you'll turn in your book to page 46, there are 6 graphs at the top of the page. Continuity means that the graph does not have any gaps or holes in it, that you could draw the function with a smooth line, never lifting up your pencil point. So if you look at the first graph, you can see that there's a hole in the graph, and that hole in the graph represents a discontinuity. You can't draw this graph without lifting up your pencil. Graph number 2 is the same graph, but it does have a point at, and we'll call this x equals c. So the first graph, there was no value for f of c. The second graph, there is a value for f of c, but it's not the same as the limit as we approach c. This is called a removable discontinuity as well. The third graph shows a step discontinuity, where the graph actually makes a jump. There is a value for f of c, but the limit doesn't exist, because as I come from the left and the right, I don't come to the same point on the graph. The next graph shows an infinite discontinuity, asymptotic to a vertical line at c, and therefore the graph goes continuously up on the left and up on the right, but it never meets because of the asymptote. The next example is a cusp. A cusp is a quick change in direction. This is continuous. The graph does have continuity. You can draw it without picking up your pencil point, but it doesn't have a derivative continuity, and we'll talk about that later. But for now, this graph is continuous. And the last example is simply a curve that has no holes, no gaps. There is a value at c. It is the same as the limit at c, and this is continuous as well. So we've seen several kinds of continuity and several kinds of discontinuity. 3 kinds of discontinuity that we're looking at here are the removable discontinuities, the ones like this, the step discontinuity, like this, where the graph makes a jump, and the infinite discontinuity, where we're looking at an asymptote. Let's go ahead and define continuity. The function f is continuous at a point x equals c if and only if 3 things occur, and it's important that you know these. This is the definition of continuity, and you'll need to be able to use this. First of all, f of c, or the value at c, must exist. Secondly, the limit as we approach c must exist. And third, the limit and the function value must be the same. So let me give you another example from our previous page. In this example, f of c exists. There is a value. Let's say it's at y sub 1. F of c does exist. The limit does exist. The limit as x approaches c is a value y sub 2. However, the limit does not equal the function value. Therefore, it's not continuous. We talked about a cusp a minute ago. Just to do a quick definition, a cusp is a point on the graph at which the function is continuous, but the derivative is discontinuous. Let me show you what we mean. So there's a graph with a cusp. You can see that it is continuous. However, if I look at the derivative, which remember is the slope of the tangent line, as we move towards, and let me change my ink color here, as we move towards this cusp, the slope very gradually increases. When it reaches the cusp, the slope goes infinitely up, and then on the other side of the cusp, it drops right down. So although it's a gradual rise towards the cusp, the slope abruptly changes direction there. One-sided limits. If you take a look at the top of page 48, you can see the definition of one-sided limits. And it is read this way: the limit as x approaches c, and they did from the left first. That minus sign says we are coming from the negative side of the graph, or from the left, of f of x. So what they're asking you to find here, let me give you an example with a step function. Here's our c. This graph does not have a limit. It has a value here and here. And if I approach this value c as x approaches c from the left, that's what that negative sign means. So as I come from the negative side of the graph towards the positive on the curve, as x approaches c from the left, the limit here is y sub 1. So it does have a left-sided limit. The limit for this graph as x approaches c from the right, from the positive side, so coming from the positive side of the graph and coming towards my value c, the limit here is y sub 2. We approach y sub 2 as we come from the right. This is from the left, from the negative towards the positive, and this is from the right. So you can see that the limit from the left is a different value from the limit coming from the right. So we can say that there is a left-hand limit. It is y sub 1. There is a right-hand limit. It is y sub 2, but the limit as x approaches c, which means from either side, does not exist. So the bottom line there on page 48 says the limit is, or L equals, the limit as x approaches c of f of x, if and only if L is the left-hand limit, and L also equals the right-hand limit. F of x, as x approaches c from the right, of f of x. So in other words, if the left-hand limit and the right-hand limit are the same, then we can say that the function has a limit as well. Please pause and look at example number 2 on page 49. As you can see, we have h of x equals kx squared, and absolute value of x minus 3 divided by 4. We're going to be using the top part of this piecewise function if x is less than 2, and the bottom if x is greater than 2. Part A says find a value of k that makes the function continuous. Well, they have plotted a graph for you here, but we know that to be continuous, these two values have to be the same. So we know that the limit as x approaches positive 2, the limit as x approaches 2 from the left has to equal the limit as x approaches 2 from the right. Alright, from the left, that means going towards 2, so that would be my top function where x is less than 2. So the limit as x approaches 2 would be k times 2 squared. The limit from the right, the limit as x approaches 2 from the right, would be using this graph because those are the values where x is greater than 2. And that would be the absolute value of 2 minus 3 divided by 4. So k times 4 has to equal 1 divided by 4. 4k must equal 1/4, and therefore k must equal 1/16. So to be continuous, the two limits must be equal. Wait, what did I do wrong? Oh, that's plus 4, excuse me. Plus 4, plus 4, plus 4. That works better. All right, sorry about that. That makes that 5, and that makes that 5/4. So there we have the value for k that would make this function continuous. Part B then asks you to plot the graph. You can do that with your graphing calculator, and we should get a place on your graph if you do your if you do your trace or even your find a value. You can find that as we approach 2, we are getting very, very close to 5 from both sides, and therefore k must equal 5/4. All right, that's it for this section. So go ahead and get ready for section 2.